In this video, we're going to go through the solution for part 2 of problem 3 of the chapter 10 lecture problem worksheets. The premise for part 2 is the same as it was for part 1. We have a batch reactor which contains some species A here that's reacting to form some species B. The contents of the reactor, we're going to say the volume is V sub R, and that's going to be constant. For the initial conditions, we're going to say the concentration of species A is equal to some Ca naught, and that the concentration of B at time 0 is also equal to 0. The only difference between, or at least in the premise, between parts 1 and part 2 is that in part 1, our reaction rate here, R, was first order, and in part 2, we're now dealing a reaction that's second order. And so what that means is that the reaction rate is proportional to concentration squared here. Okay? And since we're dealing with a second order reaction, what we need to remember is that our K here, so K, which is the rate constant, that's going to have different units. And I'll go through this for a bit. So in all cases, regardless of whatever order your reaction is, the units for your reaction rate have to be moles per liter per time. Okay? And so when we were dealing with a first order reaction, that meant that the units for our rate constant were just 1 over time. But in this case, since we're dealing with a second order reaction, that means that the units for our K here have to be liters cubed per mole per time. Okay? So think about why the units have to be that way, and make sure that you're comfortable with this sort of unit analysis. In any case, for this problem, what we want to do is we want to solve for the concentrations of A and B as functions of time, of T. Okay? So to do this, we're just going to proceed through our transient material balances and solve for, and manipulate them in such a way such that we could solve for Ca and Cb. So let's start first with the material balance for species A. Okay? And so here we're just going to write the general material balance equation. Accumulation is equal to input minus output plus generation minus consumption. Okay? We're dealing with a batch reactor, which is a closed system, so that could go to 0. And also there's no A being generated, so that's also 0. And so what we're left with is that accumulation is just equal to minus consumption. We could plug in for what each of the terms in the material balance are. For A, we're looking at the change in moles of species A over time, and so our accumulation term should just then be dNA dt here. Alright, we're going to treat it as a differential equation. Alright, for the consumption term, that's going to be equal to R times the volume of the contents in the reactor. So what we get in the end is K Ca squared times V sub R. And so the units here, they have to match the units of the accumulation term. And so what we will get is a mole per time for the units. Okay, so now let's plug in each of these terms into our material balance. And so we have dNA dt for the accumulation term. And we also do the trick that we did in part 1 of the problem to change this mole term into something that's related to concentration and also the volume. So the variables that are on the right-hand side of the equation. Since the volume of the contents in the reactor is constant, we could pull that VR out. And so what we're left with is dCA dt. And that's going to be equal to minus the consumption term. So minus K Ca squared VR. The VR's cancel, and so what we're left with is dCA dt is equal to minus K Ca squared. Okay? And so now we're just left with a differential equation we need to solve. Alright? That's a bit different from the one we solved in part 1. Now what we have here is concentration squared. So what I want you to do now is to pause the video and think about how we're going to solve this differential equation in order to get Ca as a function of time. Even though the differential equation here looks a bit different from what we solved in part 1, we could still use the same sort of separable equation solution that we've been using so far in this chapter. Okay? So let's solve for Ca. Alright, so if we could use this separable equation solution strategy, what we need to do is to break down the right-hand side of the equation into two different functions. A function that's one function that depends on Ca, and one function that depends on time. Okay? And so based on the right-hand side of the equation, what we could say is that the part that's a function of Ca is going to be the Ca squared, and the part of the right-hand side that's a function of t is going to be the negative k here. Alright? So that's how we're going to decompose our differential equation. Okay, so now let's move all the Ca stuff to the left-hand side. And let's move all the t stuff to the right-hand side. Let's now integrate this, and we're going to do it in an indefinite manner. Alright, so just to write it out, we're going to integrate this, Ca squared, and then we're going to integrate this. Alright, so the integral of the left-hand side gives us, based on the chain rule, a negative 1 over Ca. And on the right-hand side, we're going to get a negative kt. And because we're doing indefinite integrals, we also need to include our constant here on the right-hand side. Okay? So make sure you're comfortable with how to do this sort of integral. Alright? In any case, we want a function of Ca, so I'm going to rearrange this equation so that we have Ca is equal to negative 1 over negative kt plus theta naught. Okay? And so this is the type of equation that we want, but at this point, we're still not done, because we need to figure out what this constant is, what the constant here is. Okay? So at this point, pause the video and think about how we're going to figure out what this constant is. To figure out what our theta naught constant is, what we're going to do is we're going to apply the initial condition for Ca. So let's solve for theta naught by applying the IC. Alright, so our initial condition for Ca is that Ca is equal to Ca naught at time is equal to 0. Okay, so let's plug that in back to our equation. So we have Ca at time is equal to 0 is equal to Ca naught, and that's all equal to negative k times 0 plus some theta naught. Alright? And so what we end up getting is that theta naught here is just equal to negative 1 over Ca naught. Okay? So, now that we figured out what theta naught is, we could plug it back in to our equation. Negative 1 over negative kt minus 1 over Ca naught. And I'm just going to arrange this. I'll go through the algebra a bit slowly here. So I'll arrange this. First, in the denominator, I'm going to combine the terms by finding a common denominator here. So what you end up with is this. I could flip the CA naught to the top. So I get this here. And then I could pull out the negative sign from both the top and the bottom. And those cancel out. So what you end up with is this. Okay? So it took a bit of algebra to get it to this form, but now it's a bit nice and simple. But of course, we need to make sure that what we derived actually describes the system we have at hand. So at this point, pause the video and think about how we can make sure that this equation that we derived actually represents our system. To make sure that this CA equation that we derived represents our system, what we could do is we could check to see if this equation satisfies both the initial condition and also the differential equation that we started with. So let's go to a new page here. And first, let's check what the value of our equation is at time equals 0. And so let's plug in 0 into our equation. So we have a k CA naught here, and that's going to be multiplied by 0, and that is also plus 1. And so in the end, the top part multiplied by 0 also becomes 0, and what we end up with is just CA naught. So it satisfies our initial condition. Let's now check to see if it satisfies our differential equation. So dCA dt. So what we need to do here is take a derivative of all this stuff. And here, kCA naught plus, and then a time there, plus 1. And you could also rewrite the equation this way. So you could do the quotient rule, but I'm going to write the equation like this. kCA naught t plus 1 raised to the negative 1. Okay? So that here, the only part we really need to take a derivative of is this section here. And so what we do is we need to bring down the negative 1. So the CA naught's a constant, that's fine. So what we need to do now is, when we take the derivative, we bring down the negative 1, and we have kCA t plus 1 now raised to the negative 2. And then based on the chain rule, we need to take a derivative of the stuff inside the parentheses. And the only part that's a function of t inside the parentheses is this kCA naught times t. And so the derivative of that with respect to time is just k CA naught. Okay? And so if we simplify all this, what we end up with is CA naught squared over, and then there's also a k here, over k CA naught t plus 1 squared. Alright? And so this is a bit messier than what we started with, but if we take a look here, you may recognize that this part that I'm highlighting here, that's just this part squared, right? So in the end, what we do get back is k CA squared. And so our differential equation satisfies, or our equation satisfies our differential equation. And so at this point, now we have confidence to say that CA can be described by this equation. Now that we've solved for CA, let's now move on and solve for CB and derive an equation for it as a function of time. Okay, so let's now solve for CB. Okay, so to do that, once again, we'll start with the material balance. Write out the general equation. We're still dealing with a batch reactor, so there's no inputs or outputs. And for B, it's not being consumed in this reaction, it's only being generated. So that tells us that our accumulation term is just equal to the generation of B. For our accumulation term, we're still looking at the change in moles of B over time. So we end up with a dNB dt. And since we know that eventually we're going to want everything in terms of concentration of B, we could rewrite the moles in terms of the concentration of B times the volume of contents in the reactor. And assuming that the volume of contents in the reactor is constant, our accumulation term is just this. Our generation term is still just going to be the reaction rate times the volume. So what we'll get is kCa squared times VR. Alright? And so we'll put everything back into our material balance. So what we have is VR dCb dt is equal to kCa squared VR. The VR's cancel, and what we have now is dCb dt is equal to kCa squared. Okay? Alright, and so at this point we still have three sort of variables going on. We have Cb here, we have time, we also have Ca squared. Alright? And so to reduce these number of variables, we have to remember that, at least in the first part of this video, we spent it deriving an equation for Ca as a function of time. And so what we could do is just rewrite our Ca equation by plugging in this equation up here. Okay? So what we could do is just say now dCb dt is equal to the product of the rate constant times Ca naught squared over kT Ca naught plus 1, and all that squared. Okay? Alright, well in any case, this is the differential equation we need to solve in order to derive an equation for Cb. So at this point, I want you to pause the video and think about how we're going to solve for Cb. Now solve for Cb. Now the differential equation we need to solve here is a bit more intimidating than what we solved for in for concentration A. But we could still, regardless, we could still use the same sort of separable equation solution strategy that we have been using up till now, right? Because this equation here is still separable, all right? And so if we want to solve using the differential or the separable equation strategy, what we need to do is we need to decompose our equation into two functions, where one function depends on Cb and the other depends on time. Based on what our equation is, what we could say is that the function that depends on Cb, that's just 1. And then the function that depends on t is basically everything else. Right? K Ca naught squared over K Ca naught t plus 1 squared. Okay? So now that we've identified what each of those functions are, we can move all the Cb stuff to the left-hand side, and we can move all the t stuff to the right-hand side. Ca naught t plus 1 squared dt. And now we're going to integrate. So integrate dCb. We'll also integrate this thing on the right-hand side squared with respect to time. And we're going to integrate these using indefinite integrals. So what we'll get is Cb on the left-hand side. And the right-hand side, it's a little bit more complicated of an integral. So work through that. But ultimately, what you should get is the stuff on top in the numerator. That's a constant, so you could pull that out of the integral. And to integrate the bottom, you have to apply the chain rule. So what you end up with is something that looks like this. Times 1 over kt ca naught plus 1. Okay? And since we're using indefinite integrals, we also need to remember our integration constant as well. Alright? In any case, the k ca naught on the bottom here, that cancels out with a k and one of the ca naughts on top. And so, once we simplify our equation a bit, what we end up with is cb is equal to negative ca naught over kt ca naught plus 1, and then plus our integration constant. So we're on track to solving for cb, but the next thing we need to do is we need to figure out how we could solve for this phi naught here. So at this point, pause the video and think about how we're going to solve for phi naught. Just like we did for species A, what we're going to do to solve for this integration constant is we're just going to apply an initial condition to get phi naught. Alright? And so for species B, our initial condition states that CB is just equal to 0 at time is equal to 0. Alright? So let's go to the next page here, and let's apply that initial condition. And so what we have is CB at time is equal to 0 is equal to 0. And we can now plug in t is equal to 0 to the right-hand side of the equation. Alright, so we have k ca naught times 0 plus 1 plus our phi naught. Okay? And so the stuff multiplied by 0 is just 0. And so if we rearrange this equation, we end up with getting that our phi naught is just equal to ca naught. So if we plug in that information back into our CB equation, what we have is this. And then plus a ca naught. And then what we could do is we could pull out the ca naught from both of the terms on the right hand side, so that our equation now looks like this. 1 minus 1 over k ca naught t plus 1. Of course, at this point, we need to make sure that this equation that we derived accurately describes our system. So just like we did for species A, what we could do here is we could check to see if the CB equation satisfies both the initial condition and the differential equation. So let's do that now. So for CB, let's look to see what value it gets when we plug in t is equal to 0. So we have our ca naught on the right hand side, our 1 minus k ca naught, and that's times 0 plus 1. So this term, the stuff multiplied by 0 becomes 0, and what we get is ca naught times 1 minus 1 over 1, and that just gives us 0. So our equation satisfies the initial condition. Let's now check to see if it satisfies the differential equation. So what we're going to do now is we're going to take the derivative of our equation. So our ca naught times 1 minus k ca naught t plus 1 here. Okay? And really, to even just simplify this in your eyes, this part right here, ca naught times 1, that's a constant, so its derivative is going to be 0. So we don't even really need to worry about that. All we really need to worry about is this term over here. So I'll rewrite it like this. So essentially we're taking the derivative of this here. And so what we get there, the numerator is still a constant, so we could pull that out again. And for the bottom, when we take the derivative of it, based on the chain rule, we get something that looks like this. And so those negatives, they cancel out. And what we get is KCA naught squared over KCA naught T plus 1 squared. And of course, this right here is just our CA naught equation squared. And so that's the differential equation we started with. So our CB equation seems to accurately describe our system at hand. So I'll rewrite it here. Over naught T plus 1. The last thing I want to do in this video, now that we've solved for both CA and CB, is I want to plot these functions so that you get a sense of, what these equations are describing visually. Okay? So I'll draw a little dashed line here. Okay? And before we start sketching this plot, first let me rewrite what both of our equations were. So CA was CA naught over K CA naught T plus 1. And then CB here was CA naught times 1 minus 1 over K CA naught T plus 1. Alright? Before we start to sketch out what these equations look like visually, what I suggest doing is to think about, what are the values of these equations at various limits. So the two limits I want to look at, and really what I want to look at here, or what's important in these equations, is what the magnitude of this term is compared to 1. Right? Because if t is really small, that means this term is really small, and it's going to be much smaller than 1. And on the opposite end of the spectrum, if t is really big, that means that this term is also going to be really big, and it's going to be much greater than 1. And so let's think about what the repercussions of those sort of limits are. Alright? So let's think about the case where kCa times t is much less than 1. So for instance, at 0, if time was equal to 0. In that case, what that would mean is that our CA equation, and I'll write the little squiggly equals to say that it's approximately. In the case that the kCa naught t term is much smaller than 1, our equation is then basically just this, right? Where the 1 dominates the denominator. And so then CA is then just equal to CA naught. Alright, so that's at very small times. For CB, we could do the same sort of analysis. And so what we get is CA naught times 1 minus 1 over, and then 1 dominates the denominator. So that tells us that CB is about 0. Alright, let's now look at the other limit, which was the case where kCa naught times t is much greater than 1. Alright? And so for CA, that means it's going to be approximately this, because the kCa naught t term dominates the denominator. Alright? And so these CA's cancel out. What we end up with is 1 over kt. And I'll highlight here that it's proportional. This is a proportional symbol to just 1 over t. And so our CA equation is basically acting like a 1 over x equation or something like that. And to paint this even clearer, let's even think about the case where t is infinity. Alright? And so what we have is 1 over infinity, which is the same as saying that we have 0. 1 over infinity is essentially 0. For the CB term, we could apply the same sort of analysis. So what we have is CA naught 1 minus k Ca naught t, because it controls the denominator. We could simplify this out, k Ca naught, by finding a common denominator, k Ca naught t minus 1 over k Ca naught t. These terms cancel, and what we're left with a little bit of simplification, is Ca naught minus 1 over kt. Okay? And then if we apply the limit of as t goes to infinity, what we get is that Cb is approaching Ca naught. And so those are the limits of our equations. And so this information is going to help us when we start sketching out our plots. So I'm going to go to the next page. And so let's first sketch out what our Ca equation will look like as a function of time. So the y-axis here is Ca. The x-axis is going to be time. I'm going to mark off some value of Ca naught here. Down here is 0 for both axes. And I'll say that as the x-axis goes to the right, t is approaching infinity. And so for our Ca equation, we know that at time is equal to 0, it's equal to Ca naught. And then as we go towards infinity, it's going to be, 0. And we have a 1 over, our equation basically acts like a 1 over t equation. And so it's going to look like this over time, where Ca approaches a value of 0. Okay? Now for Cb, we could do the same sort of analysis, where y-axis is Cb, the x-axis is time. I'll mark off a value of Ca naught here. Okay? At time is equal to 0, we know that Cb is also equal to 0. And as time approaches infinity, we know that Cb is going to be approaching Ca naught. And our equation is going to look like this. Whoop, sorry. Something like that. Let me rewrite that. Where we approach a plateau value of Ca naught. Right? So visually, just by deriving these two equations for Ca and Cb, we have an idea of how the concentrations in our reactor are going to be changing over time. One last thing I want to show you is, if you remember, at one point when we were deriving Ca, we had an equation that looked like this, where we had negative 1 over Ca is equal to negative kt plus theta naught. Right? And if we plug in for theta naught, going all the way back here, what we could say is that we have, if we rearrange our Ca equation, we could still do this. We have an equation that looks like this. Okay? Where the reciprocals of Ca minus the reciprocal of Ca naught is equal to kt. So make sure you're comfortable with manipulating our Ca equation so that it has this form. And the reason I want to point this out is because in this form, you'll notice that basically what we have is a linear equation, where the left-hand side, we could say, is y, and the right-hand side, if our independent variable is t, the slope here would just be k. All right? And so what we could do is we could actually develop a plot where the y-axis was 1 over Ca minus 1 over Ca naught, and the x-axis was time. And if we plotted our equation like this, we would expect to see a linear equation, right? Where the slope of this line is just equal to k. This is as time approaches infinity. And the reason I bring this out is because this is actually how people solve for the rate constants for equations back in the day. They would actually linearize their data so that they could plot it in a straight line, and then whatever the slope of that straight line was, that's what the rate constant was. All right? And so even though our reaction rate had a different form, and we were working with a second order equation rather than a first order equation, the strategy for solving our differential equations was essentially the same. Just the algebra was a little bit different.